Let us continue with a discussion of some basic concepts and nomenclature. Nomenclature which will come again and again in all the forthcoming lectures during the next couple of months. Examples will be terms like training set, test set, mean squared error, overfitting, and so on. What you see here is an example of data, and these data are y with an index I. I basically just numbers the data, the different measurements, and y is the value, the response, or the material's property. So that could be, for example, the measured value being a band gap of a semiconductor. And xi of the same measurement number I, xi is the descriptive parameter, or actually the set of descriptive parameters that characterize the sample and the measuring conditions. This is considered the input for the statistical learning process. Specifically, again, for us, that could be the sample material, like say gallium arsenide or zinc selenide. It could be the space group, it could be the temperature, and so on. So in general, it is very clear that these things are not scalars. In general, we would say that x and y may well be vector quantities. But of course, for the lecture or for plotting things, I simply use scalar quantities. So what is the goal which we want to achieve? Of course, we want to fit these data, but we have something in mind. The goal is to fit the data and possibly find the underlying truth. In principle, we want to fit in a way that the fit provides us information about not existing data points, so like interpolation, but also extrapolation. And the ultimate goal of science is in finding the reason, what drives the data, what is the truth, what is the mechanism behind them. Typically, we don't know the truth. I mean, this is why we're doing these scientific studies. So typically, the truth is not known, but in fact, in this case, it is. In this case, the data are created. Y is created as a function of x, which, let me just show this, is this black function here. So a smooth function plus some epsilon of x, where the epsilon is a random noise. So in principle, the noise term doesn't need to be random, but in this case it was. And so you see the data points have some origin and they have some noise. And to find out what is really going on, what is the actuator, what is the reason behind the data point, how should we do the best fit, we should keep this in mind, that there is some scattering which may not really be caused by the original underlying so-called truth, but which may be just from some unknown, not so important noise or related uncertainties. So what are we doing in doing this? one way, and I think a very typical and very good way is to do a so-called linear fit. And so what you see here, the orange curve, is what I call the best fit. Of the data using a simple function f hat of x, which is just c0 plus c1 times x. This is what is called linear regression. This is a fit to all data points by a straight line. It has two coefficients, c0, which is the intersection of the y-axis, also sometimes called the bias, and a second parameter, c1. In principle, of course, if you would just have two data points, we could determine these parameters. Now we have many data points, and so we want to have not an exact determination, but of course the best fit. A linear equation doesn't look very interesting, very scientifically sound, but in fact it's much better than one first may think. The advantage of a linear fit is that it is often interpretable, because you only have two parameters. You could really try to find out what is behind these parameters. But also a linear fit is linear in this plot, but you should also consider that the x-axis gives you some freedom. So the x-axis, I said, is the descriptive parameters, and there are many possibilities, many components of these descriptive parameters. So one could also, in fact, renormalize or modify the x-axis using, say, x squared or the logarithm of x, or using x values from different components of these descriptive parameters. And then, of course, the nonlinearity could be put into the x-axis. This is what we think is that the descriptor, the descriptive parameters, how you choose them, is in fact the most crucial issue. They could mimic or include all the nonlinearities, and then, of course, you can do with very well justification and with a good insight a linear fit. Now, in this linear regression, what should we do? We want to determine, in general, these two parameters, determine C0 and C1, such that our function f hat of x is somewhat similar to the true values y of xi, the measured values, for I equal 1 to n, which is a subset of all known data points. So we are not using the whole information, we're using a subset, and you will see in a moment why this is really crucial and very important. This subset could be 90% of all the available data. Some people would maybe only use 50%. It should be a noticeable number of the data which you have, but you should leave some other data out for a second step, which we discuss in a second. And then, having this request, more specifically, what we are doing, we minimize the mean squared error, which we abbreviate by MSE, and which is given by 1 over the number of data points and the sum from I equal 1 to n, and then the difference between the true value, the measured value y, minus the predicted value f hat of xi and squared. So we want to find the best parameters under the condition that MSE is small. Sometimes people discuss not MSE but the root of MSE, the root mean square error, which, as the word says, is just the square root of the MSE. Or very often also in statistical learning you hear about the so-called residual sum of squares, which is RSS equals just the sum over yi minus f hat of xi squared, and also from I equal 1 to n. So it's very similar as the MSE, except of this factor 1 over n. It doesn't really matter too much which of these things you are taking. I would say for me the most popular seems to be the mean square error or the root mean square error. So these are the terms we should really keep in mind. The subset, and I should actually say the subset of all known data, and I wanted really to write this down also, pen, which is called the training set. Just right, training in the sense these are the data you use for determining the parameters or for train your model. So subset or training set are the important words here. Then mean squared error MSE, or the root mean square error, or the residual sum of squares, names, nomenclature, which will come again also later. So we have discussed that and shown it here for the linear regression, which looks okay but not too impressive, and obviously one is doing more like this, and this you see on the next transparency, where we added some higher or improved type of regressions. So the orange again, what we just have discussed, is the linear regression, and what I've added in this transparency in blue is a smooth spline regression, and in green what I would call more flexible spline regression. If you look at the data, forget for a moment again that you don't know the black curve, right? You only have the data points and you want to fit them as good as possible. If you just would naively say, I want to fit them as good as possible, the conclusion would be that the green curve looks to be the best fit. On the other hand, if for the moment, which you never do, but you would know the true answer, the blue is close to the truth. But we don't know that. Right? You only know this in this tutorial example. The black curve is never known. Now, still the question now is, how can we find out what is in fact the best option or giving us the best fit in terms of scientific modeling? And so the next question to answer is how to find out. Oops, sorry. How to find out what is best. For this we now look at the root mean square errors, and you see here on the right side the mean square error for the different models as a function of the flexibility of the model, where the flexibility is quantified in terms of the number of parameters. So the flexibility is 2 for our linear model. It is 6, I think, for the blue model. It is above 20 for the green model. So these are the number of parameters we can fit, and clearly when we look into the results, we see that the training set, this is the lower curve, has a, let's say, moderate error for the linear regression. It has a small error for the blue one and an even smaller one for the green one. So increasing the flexibility, the error clearly goes down. This is different for the other curve, which I haven't really said what the other curve is. The other curve is what you get when you look at the test set. And the test set means the data which were not used for training. So this is the true prediction, right? So looking at the mean square error for the data which have not been used tells us how good the model is really performing. It's much more important really than the training set. That the training set should be fitted well is somewhat obvious, but that the thing is also good for interpolation and extrapolation, this is what we only can find out in looking at the test set. And the interesting and important aspect here is that, again, we have a moderate error for the linear fit. We go down for the blue curve, for the medium quality spline fit, but then in fact the error increases again. This is a typical result of statistical learning. It's a very important result, and so let me note this very clearly. Okay, I had to change the settings a little bit because the desk was somewhat too low for speaking and writing at the same time, so it's now lifted a little bit. We were discussing the mean square error for the training set below and for the test set, and the important thing is that the mean square error for the test set has this typical U shape, which is, I would say, fundamental. Property of statistical learning. What does it mean? What conclusions can we draw from this fundamental property? Now, I like to discuss that in terms of my summary of what we discussed in the last 10 minutes or so. The first thing is that almost always it is true that the training error, the training MSE, is smaller than the test MSE. I think this is plausible because we did the best we can do in fitting the training data. There could be some exceptional cases where we reach the equal case, but this is very unlikely. But of course, it's not excluded. Typically, the difference between training MSE and test MSE tell us also about the quality of the fit. Related to that is then that if we increase the flexibility of the model, has several consequences. First, we get a better fit of the training data. Which of course also means we have a smaller training MSE, but we also have what we just have seen is this U shape of the test MSE. And this U shape has a very important consequence because that tells us what we in fact should take as the best quality fit. The message obviously I think is use the minimum of the test MSE. Using even more flexibility than what we have implies what we call overfitting, and that in fact is not good. Now what is behind this term overfitting? It is that the training fitting gets better, but that is because, and just consider how we started, that we have a smooth function f of x and we added an error term. What we are doing in fact, if you go beyond this minimum, is we are fitting the error, the noise, actually an error term was wrong, a noise term. So we are fitting basically the noise and not the original data. So very clearly look at the minimum that is the best you can do with the current model, with the current method you are employing. If the MSE is still too big, then I think one has to modify or change the model. So let me continue with some more statistical learning concepts, or actually nomenclature, talking about defining the terms regression, classification, categorization, supervised learning and unsupervised learning. What we have done so far was solving problems with a quantitative response, and this is called, solving problem is called regression. The important words here are quantitative, and of course that is a definition of regression. In principle, that means that we find a function f hat of x that fits the data of a given data set, which has two components: the input the feature, the descriptor x, and the output, the response y. Now, of course, not everything in life has really a quantitative output, and so there is the other option that we in fact have just a qualitative output, and if the output or if the response, that means this y values, if the response is qualitative, then we call this thing a classification problem, or a categorization. Okay, so not quantitative but qualitative means classification or categorization. In other words, it means we have also this direction xi somehow determines yi, but yi is not really a number, it's more or less a yes or no value. For example, you just asked, is this system a metal or an insulator? Of course, there are other possibilities. There's no need that it's only two values, metal or insulator. It could be ferromagnetic, antiferromagnetic, paramagnetic. It could be a half metal, a metal, and whatever. So it could be also this classification issue could be also having more than two values. It could be 5, 10, or whatever you want values. But the issue is it's not really a continuous function. It is a classification of a property like metal or insulator. Now, to determine this f function, which f hat function, which we still have to do, is we again have to minimize some error. Minimize an error. Now the error has to be defined somewhat different as before, and we define a function I of yi and yi hat in the following way. That can be 0 or 1. It is 0 if yi equals yi hat. That means everything is correct, right? So if our prediction is a metal and the data point also tells metal, then it is correct and we have what we wanted. See what is again correct. If yi is not equal to yi hat, then this is wrong or an incorrect result. And so the quantity which we have to minimize, the error, is then somewhat analogous to what we had in the mean squared error, a sum over I from I equal 1 to n, I from yi, comma yi hat. There are other possibilities as well. I think this is a very plausible thing you can do. There are other options which you could use, which go with the label information entropy or Shannon entropy, and we will discuss that during the talk later, during the lectures, not in my lecture later. But this is the simplest one, and typically I would say it works also pretty well. Let me continue with two other terms which play a big role nowadays in the field of machine learning. Supervised learning. Everything we discussed so far would be under the label of supervised learning. Supervised learning means we have features or descriptors xi which bring us to some quantities yi, and we have them also as data in the measured process, a description of the material, and like the zinc blende, gallium arsenide, and so on, and a measured property like, say, the band gap. And for this, we try to find a good fit. We try to find a function f hat of x, that this response can be at least approximated. The good thing in supervised learning is that it is possible to judge the quality. It's possible to check the quality of this function f hat of x, which we wanted to determine by using xi, yi data that were not used. In the training. This is exactly what we have discussed in detail when we said you have your data and you should split them up into a training set and data which you don't use for training, and that is a test set, and the test set tells us how good our fit really is. But then the alternative, where we don't have really this possibility, is that we have unsupervised learning. In unsupervised learning, we just have x, we don't have y. So we only have data and no hierarchy, if you want. So from x to y, I call this a hierarchy here. We don't have that. We just have data without any other information. But of course, that's actually still a very important issue, and many situations in machine learning and also in material science are of this sort. That means we are looking for structure in data. That is similar to before. Again, structure means organization. Is there some underlying organization? Which one can see is there some clustering and so on of data. But, and this is different, we are lacking information about a response, and that means, or the response, which I said it differently, which was supervising the learning process or the learning quality before. That in fact means that in unsupervised learning we don't have a possibility to talk about the quality of the result. We just have data, we don't have any way of supervising or judging the quality. Now we will have a special lecture, particular on unsupervised learning, and in fact unsupervised learning is a very hot and very important research project in material science, in machine learning in general. Let me continue in reminding and digging in a little bit deeper the question or the topic of the xi coordinate. Again, x describes the material and the measuring process, not the result of the measurement. Now the X is very important because the way you choose the X, you will see some structure in the data already. If you're not really doing this carefully, you would have, as in this case, a target property as a function of calculations in this case, or as a function of sorry, the function of measurements, and you don't see any structure. The intelligence step in all these processes, the key step in all scientific processes, is the identification of the descriptor. What should be there at the x-axis? If we choose that properly, and typically of course you do, you see a peak, and then you can start with your interpretation. If you just do artificial intelligence and you talk about data, this peak may be not visible, and then of course your fitting process, your learning process may be very unstable and very difficult. Of course, when you see this and remembering that the descriptor can be also a combination of different parameters which are used for the description, or it could be also the square or the logarithm. It could well be that this is not really just a Gaussian type of fit, but it may be actually just a combination of two linear fits. One linear, so two groups where one group basically is an upgoing line and the other one is a downgoing line. So depending on your descriptor, you can in fact find that even a linear fit, a linear regression may be good enough and telling you then the physics behind that. The important thing is you only find this linear fit if the descriptor, which is called here D2, is chosen properly. This route is often called, or typically called, feature engineering. The X parameter, the descriptor, is also called the feature. Feature engineering, finding the best feature, or in fact it's called representation learning, because in machine learning this X coordinate is also called the representation, which is used for then doing a linear or Gaussian or whatever type of fit. These are hot things, and depending really on the representation, you will be able to interpret and learn more about your system. Now let me finish this lecture, this very first lecture today, by showing you the web page of the Nomad Artificial Toolkit. This is what you will use, not today and not next week, but then in the tutorials later, that you will use to learn and maybe also modify artificial intelligence methods. So we have a web page which we developed in Nomad, where we have several examples in this web page, which are written in terms of Jupyter notebooks in a way that you can in fact even modify these Jupyter notebooks. I like to finish with actually a type of warning which says AI models are always wrong. That is something you should really keep in mind. The question is by how much? Now again, if you do supervised learning, you have a possibility, if you have enough data, to judge how much it is wrong. Very often we don't have really too many data in material science. That is another problem. And of course in unsupervised learning we never really know the quality. Now this statement, AI models are always wrong, the question is by how much, in fact comes from theory in general. So there was a statement which says theory is always wrong. The question is by how much. And because most of you are experimentalists, I should say the statement continues in saying experimental data are always right. The question is what was measured. And this is another key issue of artificial intelligence. AI and machine learning can only work if you have good data. We need to identify, to annotate our data much more carefully than we have done this in the past. Without a complete characterization, without good metadata, we are not really able to do artificial intelligence. And we were able to do this in the theory part, because we have input and output files and approximations. We know exactly what we are doing. If you say, I'm staying within the theory. In experiment, we have still to learn and to improve, to identify, to describe the details of our sample and the details of our measurements. This is something where people started only about a year ago with quite some noticeable progress, but it's something where the culture of doing science has changed, and we hope that also you will contribute to a better annotation of data, to a definition, a careful definition of metadata in what really measured numbers really mean. AI is a very powerful tool, and I underlined here the word tool. It's a very powerful tool, like in fact a chainsaw, as an example. And what I mean by this is that tools are useful if one knows how to use them, and if one knows for what they can be applied. If this is not understood, one may do more harm than good. With this, I thank you very much for your attention of the first lecture, and I think we can go to another question and answers section. Thank you very much.